We're going to start right here at the Winspear Opera House, and it's a great place to begin a math tour because we'll see that the architects, Foster & Company, were literally playing with numbers when they built this structure. And there's lots of different mathematical characteristics. If you ever happen to get a view from above the city, you'll see there's a giant hexagon in the sky on the roof of that. We can't really see it from here, so we're just going to start with one aspect of the building that you can see very well from right here, which are these louvers up overhead. And you might expect, for example, that in a grid like this, you'd see the same number of louvers in every rectangle, but as you look around, you'll see that's obviously not the case. So we're going to try to take a little look at what's going on there. But first, we'd like to understand a bit about the louvers themselves. For example, how big are they? Let's just think about their length. You know, from one end to the other of each one of these individual louvers, each one of the flaps that moves up and down. And we would like to use some mathematics to help us understand them. So how long do you think they are? We might start by guessing. How long do people think those louvers are? Just take a look up there and kind of guess.
20 feet.
I hear 25 feet, I hear 20 feet. Okay, fine. But we want to try to be able to do better. So I brought a tape measure. And unfortunately, although I am wired for sound, it doesn't quite give me the ability to fly up there and put the tape measure across one of those louvers. You know, we can't get up there, but how can we measure that louver exactly?
The windows. Use the windows. Measure the windows.
Okay, so we want to have them stand underneath the ends of the louvers. And why will that be useful?
From here, start in the end.
Yeah, right. So what we're actually relying on when we do that is, you know, whenever you're going to do math, you should have a whiteboard with you. What we're relying on for that is that we're going to create a particular shape, and we're going to use the mathematical properties of that shape to help us do the measurement. So here's the louver, way up here in the air, okay? And here we are on the ground, and we would like a line that has the same length on the ground that we could actually measure. So what shape would we like to make out of this, that we're going to be able to have that property? A quadrilateral. So will any quadrilateral do? Will I be able to? No, I need a special kind of quadrilateral. What do I need? Yeah, right, exactly. So actually any parallelogram would be good enough because a parallelogram has the property that opposite sides are equal. But what's the most convenient parallelogram for us to make? The most convenient kind of parallelogram for us to make? A rectangle. So what we'd like to do is make this into a rectangle so we can find these 2 points. We'll measure the distance here, and that'll give us the length of the louver up above. Okay, fine. How are we going to be sure that we're right underneath the end of the louver? What can we do down here on the ground that's going to make us certain that we're underneath the louver? Yeah, exactly. We can actually see right here at the base of the building where in fact, here's our rectangle right here on the building that we're going to use. And so we can see that this seam in the concrete blocks, and over there, that seam over there, not the nearest seam, but one farther over, that's exactly the length of those louvers up there. And so now we can just measure it right on the ground. And if I have a friend to help me, somebody. Well, here we go, thank you. So we're gonna go right from that seam. And I tell you what, we're gonna assume they made the blocks the same length, and we'll just measure one block. So get that right down onto the block. And here we go, and it's 14 feet. And so how long is each louver?
28.
28 feet, so actually your estimates are pretty good, well done. All right, so now we have a sense for the louvers. They're each 28 feet. Now, can we try to get some sense of what's going on with these numbers of louvers? If you look at adjacent cells, so they have these rectangles that got a long direction and they've got a short direction. The short direction is the length of the louver. So look at ones that are side by side along one of their long edges in terms of these rectangular cells up above. What do you notice about the louvers between two cells?
They vary.
Yep, obviously we're seeing different numbers of louvers in different cells. What else do we see? So in some cases, if they close, they would actually touch. So not in like the cell over there that only has 2 louvers, those are never going to touch. But in some of these other cells, they might touch or even overlap. Yeah, excellent observation. What else do you notice about louvers in 2 adjacent cells?
They're attached
Exactly. Anytime you've got one louver, if there's more louvers in the next cell, the ones from where there's fewer louvers go right through and attach in the same axis. So that actually tells us something about the numbers of louvers that could appear, because each one of those louvers from the cell that has fewer goes straight through. So I'm going to draw on here as if I had a couple of cells. So here's one cell, and here's the next cell. And like if I take this one that's got 3 louvers across, well, we know these continue. So we're going to have at least 3 louvers over here. And so you'll see there's 3 and then 3. But then there's more in the next cell. And how many more? Could it be an arbitrary number of more? What do you notice about the way the louvers extend into the next cell? It's always in between, and I heard doubles. So now if I put one louver in between each of these louvers over in this cell, will that double the number? In other words, does it go from 3 to 6? Take a look up there. 7. Why does it go from 3 to 7 if you're putting one in between each? Why wouldn't that be double? Yeah, because if you draw 3 lines in a rectangle, it breaks it up into 1, 2, 3, 4 spaces. So you actually will be getting 3, if I want to do it here, you'll be getting 3 plus 4 times 1. Where did that 1 come from? Because you added 1 in every space. Can anybody see a place where a different pattern was used to move from one cell to the next? Yeah, what do you see over there? Yeah, inserting tube in every space. So we'll start over here with 2, and then what happened is those continue into the next cell, and we have 2 added in every spot. Okay, and so now we get the number pattern that we go from 2 to 2 plus 3 times 2, which is equal to what? It looks like 8. Okay, excellent. And you'll see, if you look here close to the building, the same thing is done with 3 of them. Okay, where these continue, and then we add 2 between every one of those, and so now we're going to get 3 plus 4 times 2, which is what? 11. Excellent. But now if you look way down at the other end, we take these 11, and it actually lines up with 5 on the other side. And we put 1 in between each. So we can see from this direction we're getting 5 plus 6 times 1 also equals 11. So you can see that the architects are playing with numbers and different ways of breaking down the same number using simple elementary arithmetic. So it's kind of fun to see how we start with 5 on one side and 3 on the other, and then using these 2 different ways of sticking extra slats in the middle, we come together to form the number 11 in the center. So I think that's something that the folks here will enjoy, to think about the different patterns of numbers that were used to create this building.